a second. Okay. Yeah.
Super. Okay, so we're really delighted to have and I forgot to make sure I pronounce your name correctly. I will try, and you will correct me. Petja Paakkinen.
Excellent.
Perfect. To speak with us today. He obtained his PhD from the University of Jyväskylä in 2019. Afterwards, he spent 2 years as a postdoc at the University of Santiago de Compostela, and he is one of the authors of EPBS 16 and EPBS 21 global analyses of parton distribution functions. What's the thumb suck on the number of citations for those two works?
I cannot remember right now, but
hundreds at least. So
I guess
really delighted.
Yeah. The 21 version is quite recent, so it doesn't have that many citations yet, but we'll see.
Yeah, I'm sure we'll have very many. So really, thank you very much for taking the time to come to speak with us. He currently works as a postdoctoral researcher at the University of Jyväskylä in the Center of Excellence in Quark Matter. Really delighted to have you. Thank you for coming to talk to us and introducing PDFs and nPDFs to us. Please take it away.
Okay, thanks a lot for the very nice invitation to give this talk. And since I got the impression that you have quite a diverse audience, also in the sense that some of you have been in the field longer than others, so trying to be like easygoing with the newcomers, this should be quite a starting everything from the basics. There will be some more technical slides, but because I still want to try to be precise on all the definitions and such. So, but if there's something which seems very technical, just ask me, and also then maybe after a couple of slides, I'm returning to more basic stuff. So let's see how it goes, and at any time you can ask questions. So what we are after when we study PDFs, that stands for parton distribution functions, is let me see. Okay, works like this. Is the structure of matter. So we have currently a very good understanding of the subject. So we know that all the basic matter constitutes of molecules, which constitutes of atoms, and so on and so forth. We have the atoms constituting of nucleuses or nuclei, which are made of nucleons, and they are built together from quarks and gluons. Okay, but how do we resolve this structure of matter? And in particular, how do we do that on the smallest length scales? Okay, well, we physicists have known the answer to this question for a very long time. So you most likely remember the Rutherford experiment where the nucleus was found. And the idea was that if you have something that you don't really understand, you just hit it with something and see what comes out. Usually this gives you some new information about the thing that you're trying to study. Okay, so when we want to, let's say, study the contents of the proton or what's it made of, we can take, for example, an electron and accelerate it to a large momentum k, and then collide it with the proton with momentum p. And what happens is that if the collision energy is large enough and the electron scatters with a large enough angle, then the electron starts to resolve the insides of the proton. And what can happen is, for example, that the electron meets a quark from inside the proton, and then they scatter mediated by a photon, and then the electron and the struck quark fly apart. Well, of course, the quark that was hit cannot carry all of the momentum of the proton, but it has some fraction of the momentum, and we label this as x. But now, if we want to be more specific about what is it that we are actually studying with this kind of processes, we need help from theory. So we know that there is a strong interaction which holds together these protons. That's what we have learned from experiments like this. And after some thinking, we have found a theoretical basis on what's going on in here. So this is what I'm going to describe next. So this is one of the more technical slides, but then I return back to that very basic process. So we have a concept called collinear factorisation of QCD. So QCD stands for quantum chromodynamics, which is the theory of strong interaction. And in this collinear factorization, what it means is that if we have a cross section, which means well, collision probability, a cross section for producing some final state where we measure the k of the final state, and then there can be anything else in addition. Well, this can be described as a convolution of a couple of things. So there are so-called coefficient functions, which we are able to calculate from our theory of quantum chromodynamics. And then there are the parton distribution functions, which on the other hand contain well, long-range physics and describe the structure of the struct objects, and this we cannot calculate from our theory directly. In addition, there can be so-called higher twist corrections to this, but if we are at high enough momentum transfer scale, so for example, in the case of the previous process that I showed, the electron scatters at large enough angle and has large enough energy, then these are very much suppressed, and then what we need to care about are these coefficient functions and the parton distribution functions. Now these PDFs, short for the parton distribution function, they depend on the hadron or nucleus that was hit, and also on the parton flavor. We'll come back to this later. And also on the x, which I introduced in the last previous slide, which is the fraction of momentum that the parton carries of the parent particle. And then they also depend on the factorization scale, which and the evolution of these PDFs in terms of this hardness of the process is governed by so-called D-club equations. But the very nice thing is that these PDFs are expected to be universal and independent of the process that we are looking at, so independent of the coefficient functions. And now what I kind of want you to remember from this slide is that this is the framework upon which every PDF analysis and application relies on and also tests further. So when we apply this factorization to some process that we want to study, then we are like assuming that this works, and when we compare to data, then we can learn new things and see if it works really. Now, I want still to remind you of that the PDFs are not a full picture of the, let's say, the hadrons or the nucleus, but they give you only description about the longitudinal momentum distributions within the hadron or nucleus. So this can be also extended to other kind of objects. So we are now standing here where the PDFs are, but we could also have more complex distributions which tell also about the transverse momentum of the parton. Or we could go to another direction and talk about impact parameter distributions, which tell you about where within the transverse profile the struck quark was originally. And these are linked to the GPDs, so generalized parton distribution functions, which I believe Petja Paakkinen gave you a talk just recently. So I wanted to remind you of this bigger picture. And also it's important that all of these objects and their factorization have a region of applicability. So you study some of these in certain experimental observables, but there are limitations. So you can just take a process and say object that you are interested of, but you need to go into the theory, look at, if I take process, what is the object that I'm probing with this kind of a process. So let's get back to the very basic processes and this kind of electron-proton scattering that I showed in the very beginning. So I said that we cannot calculate these PDFs directly from the theory with our current methods. Maybe in the future we learn how to do this. For example, there are progress in how to do this in the lattice. But currently we obtain these from comparing to experimentally measured processes. And the idea is very simple. So if we understand our probe and after the scattering, we measure something very precisely, and we are able to calculate from our theory what is going on in the scattering process. Then, based on this information, we are able to deduce what was inside the, let's say, proton, and how the constituents that were resolved in this scattering share the momentum of the proton. But now, well, this kind of a simple process is very nice, but it's not enough. Actually, we need to do everything everywhere and all at once. Well, let me explain. So the process that I just described is that of deep inelastic scattering. So now drawn somewhat differently. So here is the lepton that I previously showed as an electron, which comes in and scatters from a hadron. And then we take a quark from the hadron, and the lepton and quark interact by means of either a virtual photon, Z boson, W boson, and then the struck lepton flies off with some other momentum. Now, let's say we take the photon-mediated case. Then we can write the cross-section in this way. We have the coefficient function, and then we have a sum over the PDFs of the hadron. And the nice thing is that just by looking at the external kinematics, we can access the scale of the at which we are probing the PDFs, and also the momentum fraction. So in this sense, this is a very nice process. But it's not enough, because we are summing over all different PDF flavors. So with this process, we can only have like a picture of the average behavior of the quarks within the, let's say, proton, if that was our hadron. But we want to do studies in more detail. So in order to do that, we need more processes. And we can, of course, use or study cases where the mediator was not a photon, but a Z boson or W plus or minus, and that gives us additional information. But we can also look into other types of observables and processes where we can have even more information about the contents of the hadron. And one of these is Drelian, which happens in collision of two different same or different hadrons. And here you take a quark from both of the hadrons, and they annihilate again via a photon or a heavier boson. And then we measure the leptons which are generated in the final state. And now again, if we take a photon-mediated process, we can write it in this way, where we have sum over the different quark flavors. But now it's like a different combination in general than we had in the DIS process. So combining this information, we learn again new things and more things. And now we reconstruct the momentum fractions of the initial state quarks, again from the final state observables, like the invariant mass of the final state leptons and also their rapidity. But we can go even further at new processes, and also very important are processes where instead of leptons, we are measuring hadrons in the final state. So for example, let's take inclusive hadron production. We have two hadrons in the initial state, and then there is a hard scattering process which produces a third hadron in the final state, which we measure. Now, in this case, again, we have a coefficient function which we can calculate from our theory, and we have the PDFs of the initial state particles, but now we need to also take into account how a struck quark hadronizes into something that we can observe, so this final state hadron. And this is done in the collinear factorisation in terms of these parton to hadron fragmentation functions. And why we want to study these kind of processes is that now also gluons enter the cross-section at leading order. So in this way, we get access to new details about the contents of the hadrons. The penalty that we pay is that these fragmentation functions, they now produce new source of uncertainty in our extraction of the PDFs. One can try to go around this problem by, instead of measuring single hadrons, by measuring jets. So, and these are like collimated streams of particles in our detector. So now we don't. So now this is kind of easier to calculate in the sense that we don't need this parton to hadron fragmentation function, because we are trying to capture the kind of whole evolution from the single parton to a full jet that we observe. But there are other kinds of complications that arise from this. So first of all, we need to have some definition of the jet, and this definition needs to be infrared safe, meaning that, well, we should be able to calculate this process to all orders in our perturbation theory. And also, well, that's not enough, because what we calculate in our theory are like parton jets, and what is observed are hadron jets. So there's a bit of a mismatch, and so you need non-perturbative corrections to describe this, which are often taken from well, general purpose Monte Carlo generators. Okay, so many details going on, but so we need many different processes in order to probe different flavors. Also, we need to do this kind of everywhere, because we need a lot of data in order to probe the PDFs in a precision level. And this is what is done in this global analysis. So here's an example from the data included in the quite recent CT18 PDF analysis of the protons. And what they do, they combine a lot of data from different experiments. So we have, for example, Hera in Germany, and also a lot of data from CERN and maybe Fermilab, things like this. So like a very global analysis, data from everywhere. And from different kinds of experiments. So one important part are fixed target DIS and Drellian experiments. And these are important in setting the large X quark distributions. And by combining DIS and Drellian, we have access to like the flavor separation. And much of this data are quite old already, but there are still new data coming from Fermilab and JLab. And for example, recently the Sequest collaboration released new data, which help us better understand how well what is basically the difference between up and down and anti-quarks within the proton. So very, very interesting. But these kind of things are not enough. Fixed target means that you have a target at rest, and then you have a probing particle coming in, either electron or proton or even a pion. But this means that you cannot access very high energies, and then due to this you cannot reach very small x or very high q squared. So we need other types of experiments. Let's say take a collider, and very famous one is this Hera, where we collided electrons to protons that both had very large momentum. And now you can access very small values of x and like very tiny details of proton, and we have very nice data ranging in x from almost 1 to less than 1 part in 1,000, and also covering a large lever arm in Q, which also helps to constrain the gluons through the D-clap evolution. But then we want to have even more, and then we have these hadron colliders, which again give access to new processes like W production, Z production, jets, very importantly, and even top pair production. And here I'm showing just as an example data from CMS, where they measured in a triple differential manner jet production, and as you can see, our theory matches with the measured data in over many orders of magnitude in the cross section, and like a couple of orders of magnitude in the transverse momentum of the produced jets. Okay, very nice, but we cannot do this like we first study one thing, then we move to another, and then we take another process, see how things work there. But in order to have a precise understanding of the contents of the proton, we need to kind of use all of these data and understanding at the same time. And this is what I refer to with all at once, or you should at least do it as fast as you can. And this is the essence of the global analysis. So what you need to do is that you start from by defining a functional form for your PDFs. So this is just a choice, and you can try to improve it after the analysis, but you need to pick something because this is a function, you need to parameterize it in some way or another. And you do that at some initial scale Q0. When you have done that, you can set first ansatz for your parameter values of your parameterization. And this gives you now the PDFs at your initial scale. Then you take the splitting functions, which enter the dclap, and this you have calculated from your QCD theory. And you solve the dclap equations to get the PDFs at higher scales. Now, when you have done that, then you are able to compute the observables that you want to study. So you combine these PDFs at all the scales that you need, and take the coefficient functions that you have also calculated from your theory, and combine these to calculate the observables. After that, you can compare with the data from experimental measurements of these observables that you want to study. And you do this in a global manner. You take all the data that you have and compare them to your calculations, taking into account also the correlations between your data values. And you combine these differences into a chi-squared value, which tells you how good the fit was. Then you ask the question, is this the smallest possible chi-squared that I can access? Well, to answer that, you need to vary your parameterization. So you take another loop, see if you have reached a minimal value. If not, you do it again, every time changing your parameter values a bit, and you go over and over until you think, okay, this is now the smallest value that I can access, and then you declare that now I reached the best fit of my PDFs. And is there a question or something else happening?
Just background noise.
Okay, very good. So and then you can proceed to uncertainty analysis of your results, but let's forget about that now. So this is the global analysis way to access the PDFs. Well, what do we learn?
Questions.
Question, okay.
Yeah, sorry, on the previous slide.
Yeah.
So to start off with, you have to pick a functional form for these PDFs at some scale. What goes into that? They can't just be some arbitrary function, right?
Sorry, can you repeat the end of your question?
So what goes into selecting the functional form of the PDF at a specific scale? Because it's, we can't do it determinatively. So how does it?
Well, you take a guess from phenomenology. So you know how your cross sections kind of look like when you measure them, and you think, okay, this might mean that I need to use this kind of functional form for my PDFs. In principle, you want to be as generic as possible, so allow as much freedom in your functional form as possible. So that means allowing for more parameters in your fit, but you cannot go to like millions of different parameters if you don't have the data. So you need to adjust your functional form to how much you have data, how good your way of solving this loop is, because more complicated you make this parameter space, the more time you need to like go through and reach the minimum. So it's a intense computational problem, and all of this guides you to select a functional form that is flexible enough, but also does not have too much freedom in the regions with which you cannot really fit. And also there has been progress from group nPDF, where they use like neural networks in order to like bypass this problem that you by hand choose some specific functional form. And then you, well, use like machine learning in order to look out for what the functional form basically should be. Okay, was that good enough? Okay, so let me continue then. So if we go to thinking about these PDFs in a very basic terms, they are kind of like probability density functions for finding this some parton I within the proton, such that it carries some fraction of the proton's momentum. It doesn't quite hold to higher orders in perturbation theory, but this is like the basic way of thinking it. So then if we take our measurements and we deduce what our PDFs are, how they look like, then what we learn about the proton structure based on these. Well, let me go through some very basic examples. And now I'm sorry here, I would like to credit the author of these pictures, but I cannot remember anymore where I take them. So these are not mine, but they are very nice pictures. So thank you, the author. Okay, so let's take a very simple example. If the proton was a point-like particle, then there is no other chance than that the point-like particle carries all of its momentum. So then we would see that our PDF is just a it is centered at one, and there is nothing else. Well, that's not the case. We know that there are at least 3 quarks in there, and if they would not be interacting at all, well, then they had to still fly at the same speed in order not to like fly apart. So all of them had to have just 1/3 of the proton momentum. But that's not the case either, because then even a small perturbation from outside would let the quarks fly apart. So that's not the case. We need at least some interaction between these quarks, and so maybe they are held together by just a few gluons. So then it would be like this rubber band model, where in some times one of the quarks has a bit larger momentum, which it borrowed from the other quarks, and then later on in time it was pulled back kind of, and then has a smaller amount of momentum. But in general, we are somewhere around the ballpark of 1/3 of momentum fraction. But what we find from this global analysis is that actually there needs to be more. There are some quantum fluctuations which kind of evolve the state of proton from one point in time to another, and there can be one quark can emit a gluon, which can then split into two gluons, and one of them can split into quark-anti-quark pair. So there can be like a very different configurations of the proton at any single period of or interval of time. And by going to larger energies, and which means that we can access smaller momentum fraction, by this way we can access these smaller fluctuations. And we see that there is actually very rich structure within the proton. Now, of course, we have different flavors, so different flavors carry different amount of the momentum. And so if we look at the very large X, let's say more than 0.1 of the momentum fraction, then we see that our traditional picture of the proton is actually very good. We kind of 2/3 of the momentum is shared by up quarks and 1/3 by d quark, and then there are every now and then one or two gluons flying around. But then when we go to very small X, this like richer structure emerges, and we start to see this anti-quarks coming from the quark-anti-quark splittings, and also strange quarks, maybe even charm quarks every now and then. So if we change our perspective and look at this in the logarithmic scale, now we see better that when we go to small X, actually we have mostly gluons in there, and also few quarks. And then we have to remember that this picture changes also depending on the resolution scale at which we are looking into these PDFs. So when we take kind of a very hard scattering, or this is not extremely hard, but still a hard scattering. So if we struck with an electron and it scatters with a large angle, large energy, then the proton looks like something like this. But if the scattering was less energetic, then we would be probing the PDFs at a smaller scale, and there they look actually a bit different. So we would see less gluons and also less quarks at the small X. And what governs this scale dependence are the D-Clap evolution equations. So we can always take a smaller scale and then use these equations to see how things look at a larger scale. And what you can also see from here is that these different flavors can have large uncertainties. So these uncertainties are pictured in these bands. So we know that, for example, that there should be strange quarks at small x in order to describe our observed processes, but there is a large uncertainty in how much exactly we need them. And also when we go to small scales and small x, then our gluon content is also has uncertainty still. Well, these were the PDFs. Now let me switch to nuclear PDFs. So instead of having a proton as a target, we can do the same for nuclei. And if one would simply assume that, okay, nucleus consists of protons and neutrons, then how different can this be? You just pick a proton from inside the nucleus and then you struck with a quark within it, and it should look the same as a free proton. But this is not the case. Nature tells us that something has changed. And when we do this kind of measurements with the heavier nuclei and compare them with the, let's say, deuteron, which is very lightly bound state of a proton and neutron, there are large deviations from unity. If what we measure would have been at unity, then we could have said that, okay, proton within this nucleus was exactly the same as a free proton. But this is not the case. It seems like the PDFs of a bound proton are very different from those of a free proton. And we see effects like the Fermi motion at very large values of x, then go into EMC effect and anti-shadowing enhancement, and at very small x we have shadowing. Let's come back to this a bit later. Okay, so many of you study like nucleus collisions or proton-nucleus collisions where these things are relevant. But one thing where we also need to know how the PDFs are modified in nuclei is due to that we want to understand the proton better. And currently it is the case that actually neutrino nucleus DIS data have been used both in proton PDF fits and in nuclear PDF fits. And this is kind of a problem. But what the case is that usually analyses which use this neutrino nucleus DIS data have found that there is a suppression in the strange content of the proton compared to that of up and down C quarks or anti-quarks. So since all of these are like light quarks, we would expect them to behave quite similarly. So if you construct a ratio like this, you would expect it to be at 1. But when you take nuclear neutrino nucleus DIS data and try to constrain the proton PDFs with these, you see that there are less strange quarks. Well, later then it was found at Atlas that if you take just electroweak boson production data and see how much strangeness there would be within a proton, you are around unity. And this was a new thing, came as a bit as a surprise, because everyone had thought that, okay, we can just anyway use this nuclear DIS data, correct for the nuclear effects in a way or another, and everything works fine. But now this complementary data have now confronted the earlier view, and it's still an open question should we use the nuclear data in our proton PDF fits or not? And if, then how to correct for the nuclear effects? And these corrections are done differently in different proton PDF fits. So nPDF, for example, have found that depending on whether they correct their analysis with uncertainties from nPDF 2.0 nuclear PDFs or not, it changes their results for some aspects of the proton PDF fit. But still they decide to include the nuclear data because this gives better constraints to their analysis. Then other analyses like MSHT, they use nuclear corrections from DSSZ, nuclear PDF analysis, and use additional 3-parameter fit, and CT18 uses a scale-independent phenomenological parameterization. To me, this all tells just that, well, we need to understand the nuclear modifications and do that better if we really want to understand the proton also. And so how do we access these nuclear PDFs? We could use some model telling how the nuclear effects behave, but what we have been doing, for example, in Jyväskylä, is to just take the global analysis. In similar way as with the proton PDFs, we take the data that is available to us and try to fit our nuclear PDFs to that. And by doing so, we are relying only to the QCD collinear factorisation, and we are trying to be model agnostic about what causes these nuclear effects, and just see, well, does the collinear factorisation work with the nuclei, and how well, where it might break down. And if everything works fine, then we are very happy we have a good description of our nuclei in terms of the parton content. Yes. And what has been a very good progress in this field recently has been that we have new data from LHC. So we have dijets, W and C bosons, D mesons, which enter our analysis. And well, how do we parameterize then our nuclear PDFs? I'm just showing one way which is used in our analysis. So in this case, we define the bound proton PDFs, which we take from the free proton PDFs by applying a nuclear modification function to them. And this product gives us the bound proton. And the nuclear modifications, we take a phenomenologically motivated form. So at small x, we have this shadowing, then anti-shadowing EMC effect Fermi motion. When we have the bound protons, we use the isospin symmetry between proton and neutron and construct the full nucleus. So this is what then enters our calculations for the observables. And in parameterizing these nuclear modification functions, we also assume that there is a power law type of function governing the mass dependence of the nuclei. Okay, very nice. Now I thought I'd just show quickly a couple of observables which we use in our fits and which have helped us constrain the nuclear PDFs. So for
example, Petja, would you mind if we looked back a little bit more on the core, really the core of what you're doing? Okay. So I just wanted to, I didn't quite catch. So we parameterize the X and A dependence of R. So you very nicely pointed out, for example, in PDFs that the PDFs satisfy a DGLAP evolution.
Yep.
So that tells us how the FIP changes in q squared as we change q squared from some initial q squared. And I see here we have these r's on the top line that also depend on q squared.
Yes.
So are the r's also going to evolve in q squared? And if so, is it in some controlled, say, DGLAP-like way?
Yeah, exactly. So we take just the DGLAP. That comes as a part of the let's say the collinear factorization framework. So it describes how some partonic system evolves into a different one when you increase your scale. And now what we kind of assume here is that this applies both to the proton and to the nuclei. And where we apply it is that in free proton case, what really enters the cross-section formulae are the free proton PDFs. So that's natural. We apply the DGLAP evolution there. This is the kind of physical object which we want to evolve. Now in the nuclear case, what enters the cross-section is the parton distribution of the full nucleus. So what is done is that the parametrization of this this nuclear modification is done at the initial scale of our evolution. So we apply this initial scale nuclear modification to our free proton PDFs, and with this we calculate our PDFs of the full nucleus at the original scale. Then we use just the typical DGLAP evolution to evolve the PDFs of full nucleus to larger scale. And then we can kind of reverse this process. So based on our evolved PDFs of the full nucleus, we then solve how this nuclear modification changes. Okay, so this is where we get the evolution of nuclear modification from. It's just DGLAP. We assume that DGLAP works everywhere and there is nothing else. Then later data will tell is this correct or not. And maybe I can point out that how the DGLAP evolution affects these nuclear modification functions is that it shrinks these effects. So if at my initial scale I have shadowing suppression at like 40%, then when I evolve these effects to larger scales, it makes this difference to unity smaller. So at some scale I have then 20% and at higher only smaller effects. So in this sense, what we it's easier to see these effects in observables at smaller scale. But then of course you still need high enough scale that you believe that your factorization works. So this is we want to go to smaller q squared in order to have bigger nuclear effects, which helps us constraining, but we need to keep in mind our limitations. So at too small q squared, the factorization would break down. The higher twist effects would be just too large. Okay, I went a bit too but I hope this answers your question.
No, that was fantastic. Thank you. But Herbert, I think, has a follow-up.
Yeah, generically, I mean, the direction this seems to be going sounds reasonable, right? You would expect that if your objects look smaller, they look more independent, right? They don't overlap that much, and therefore these nuclear effects should decrease, right? In some way. So to me, that sounds kind of reassuring that it's going that way. If it had gone the other way, I would be really worried.
yeah, it would then it would be, well, yeah, you're right. Excellent. Yes, I fully agree. Yeah. Okay. It seems that I spent more time here than what I thought I would. So I'll come back to these observables next week when I discuss them in more detail. So I'm going very quickly through this. So we have measurements at LHC, for example, digit production. And what we like to do is to take these ratios of measurements at proton lead to those at proton. And in this case, we have this, well, double ratio, where the idea is that in each of these ratios, there is a cancellation of the hadronization and luminosity uncertainties. And so we expect these non-perturbative effects of the jet production cancel out. Nice. Then when we take the ratio of these ratios, we expect cancellation of the free proton PDFs. And so that the final observable would depend only on the nuclear modification functions. Okay, this is the idea. And it works pretty well. And with this data, we have a good access to nuclear modifications, especially of the gluon from kind of small x to larger one. And what we find in our fit is that we get pretty good fit, except a couple of data points at the very forward direction. But these data give very good constraints on our nuclear PDFs. And if you compare here the uncertainty bands from EPBS 16, shown in gray, to those from EPBS 21 in blue, we have a very large reduction in our uncertainty due to this data. Then we include also the D0 production. So this is single hadron production. We need to take into account the hadronization effects, so the fragmentation function. But again, if we use this kind of a ratio, we then expect that the fragmentation function cancels between the proton lead cross section and the proton cross section. And these are now in the backward direction, so that is the lead going direction of the collision. And again, very good fit, but not so much reduction in the uncertainty, because this is the large X of the nucleus, so then it's already quite well constrained from other data. But then if we go to the forward direction, we see again a very large reduction in our uncertainties by using this data. So the D0s are very important in the forward direction in reducing our uncertainties of the gluon. And we have also W boson data. And again, these are now from the 8.16 TeV data set, where well, there is no proton measurement at the exactly same energy, but what we have done is that we construct a ratio between the 8.16 proton lead measurement and 8.0 proton measurement. Again, we get a good fit, and in the forward direction, we get some reduction in our uncertainties, but this is also now the region where the digits and D0s play an effect in constraining the PDFs. So and it seems all just consistent, and this is very important check that our factorization works also for nuclei, and they seem to be universal from one process to another. Okay, then I will quickly show what we learn in terms of the nuclear PDFs. So here on top, I'm showing the results for the lead parton distribution function in below that for the proton, and here is the ratio of the PDFs in lead compared to that of a proton. So what we see is that for up and down quarks, we find there must be some Fermi motion effect. We see a very clear EMC effect. Seems like there is some anti-shadowing and there is some shadowing at the small x. Very clear. And the UND seem to be modified in a similar way. What I say shown here. And when we go to up and down anti-quarks, it seems pretty similar, but now we have a much larger uncertainties at high x. And maybe there is not so much anti-shadowing on these, but we would need more data in order to constrain these better. Then when we go to strange and charm, we have larger uncertainties here, especially for the strange quark, very difficult to constrain. And there is just not enough data that would be directly sensitive to just this flavor and nothing else. So this is a problem to constrain better. The charm quark.
Yellow is charm, right? Because that's the C is very faint on there.
Oh, right. Yeah. Sorry about the color. It doesn't show very well in all screens. So I would need to update the slides with a better color. But if you can see it, it's going here, and it has actually smaller uncertainty than the strange, which is due to that it's perturbatively produced. So we can actually mostly calculate how it comes to being in the scale evolution, and it actually follows very much in detail the nuclear modification of the gluons. So because charm is produced like gluon to C bar splitting, so then also the nuclear modification of charm follows that of the gluons. And now with our LHC data, we are seeing very good, or finally are having good constraints on our gluons. And it seems that we can confirm there seems to be anti-shadowing and also shadowing at small x on our gluons. As a very final point, well, these were the results in our ePPS 21 fit. So then if we compare to what other people have gotten in similar analysis, the nPDF 3.0 agrees very well on the small x region where the d zeros in the forward direction are constraining the fit. But then we have quite large differences in the large x region. NCTEC group has also released fits, and here we see that now we are in better agreement at large x, but then at small x we have differences with our results and the nNPDF compared to NCTEC, which is kind of surprising since all of these are using the forward D0 production data. And this is something that I was planning to talk about next week, go into more details why we find differences like this. So I went, okay, well, thank you a lot.
That was really super. Thank you. We had questions during, but happy to take questions after. Cole first, I think. Please go ahead.
Hi. I just wanted to ask. I think at some point you said that your fits shouldn't be. You don't expect final state effects to be important. And it wasn't obvious to me why that is. Like, for example, some of the ratios look very similar to how you would define a nuclear, like an RAA, or maybe even exactly the same. I was wondering. To extent, if there is final state effects, would they kind of just be captured by the fit, or would you be able to see that something was breaking down in your fits like it wouldn't? Does that make sense?
Yeah, okay. I had bit difficulty in hearing, so but you I think you referred to this slide,
Yeah.
I guess. And so what is the expectation here is that if we just take the proton data, and then this is like a self-normalized cross-section. You take a double differential measurement, and then you integrate over the rapidity dependence and divide your results with that. So your non-perturbative effects appear both in the upstairs and in downstairs. And what the people from CMS demonstrated in one of their talks is that the effect is linear or is constant at with respect to rapidity. At least this hadronization uncertainty or hadronization effect that they calculate from Petja event generator. So, and then if you take this kind of a ratio, the hadronization effect cancels out. Now the assumption is that the same happens also for the proton lead case. This hasn't been studied in detail, and we have hopes that people who are now extending Petja to, so it's this Angantur kind of thing, where they would be better able to describe, for example, proton lead collisions. They could study this in detail, see if the same applies for the proton lead data or not. Currently, this is a assumption, but at least for the proton part, this works very well. And then it's a question, how well do we actually trust this in proton lead? But we don't have any calculations about how large these non-perturbative effects should be, and so we cannot currently say how good this assumption is. Very good question. Yeah.
Okay. Yeah. Thank you.
Super great. Bart.
I just wanted to ask, why aren't PDFs calculable from theory? Or what about PDFs make them so that you can't find directly from theory? You have to sort of do this, you have to use experimental data to sort of find PDFs. It seems to me, I'm probably misunderstanding, but it seems to me that the D-galactic equations sort of give you a way to find PDFs in theory.
Yeah, well, for the D-galactic equations, you need to have the PDFs at some scale. And then you can, of course, try to push to, if I go to very beginning, try to push to smaller scales, but then you have these higher twist effects, which complicate the picture. So this whole thing works only at sufficiently high scale. And the complications come from the non-perturbative aspects of QCD. So you cannot use perturbative tools, or at least we don't know sufficiently powerful tools to shape our perturbation theory in such a way that we could calculate the PDFs. People have tried to do this in lattice calculations, and the problems there arise from I'm not an expert on this, but there is some difficulty due to the definition of the PDFs in terms of like matrix elements, and the fact that these are collinear objects which are defined on the light cone. And what people have done is that they have then used a definition of an object which is kind of similar but not exactly at the light cone, and then they extrapolate to the region where this object should match with the PDFs as they are defined. So what people are trying to do is that they define these quasi-PDFs or pseudo-PDFs, and and then measure them on lattice calculations and try to extrapolate to PDFs. And there is very good progress, and the results seem to be agreeing with what we get from global analysis. So, and perhaps in the future, we, as soon as we establish that things are done correctly and at very good precision, we could use this lattice data to constrain, for example, the strangeness, which is currently difficult to constrain.
Thank you. Super. Herbert, did you want to ask?
Yeah, maybe just a quick one. I'm guessing you would naively expect that what you saw for Tron following the gluons would be more pronounced for bottom, but I guess there is very little data in that corner of phase space where you could access anything there with heavier quarks.
Well, once you go to high enough Q squared, then you are accessing scales where the bottom quarks are a part of your calculation.
Yeah.
Well, and then you see that, well, you need them. They have to be there, and just calculating them from your perturbation theory seems to work fine. I was thinking I will talk a bit about heavy quarks next week also, and how the scheme dependence of this object enter the problem. So
very good.
I would imagine that LHCb has a fair amount of data on proton and proton-led beam meson production.
I would guess that LHC is probably the thing to go to at this point, right? I mean, all the experiments probably less so.
Yeah, exactly. And yes, there are data which have not entered our analysis yet, but my colleague here in Jyväskylä, Hannu Paukkunen, has been studying exactly this. I'm not sure if the paper is out already, but might be even that they released new paper this summer. I need to check that, but yeah, you can calculate the bottom production and compare to the data. So
Very nice.
Very good. Very good.
Yeah. So okay, two things. First, I noticed that you get lower numbers of gluons than you would expect at that small x, right? When they're in the nucleus, do you have a feeling for why there is why do bound nucleons have lower numbers of gluons for a given x?
yeah. Okay, so let me go back to that.
Well, for small x, that's what I saw. Right?
Yeah. So some of these nuclear effects have been described by different models, and this small x suppression is one of them, and where the name for this shadowing comes from is actually, well, one of these models, or the way how we understand this effect in terms of models, and that's related to like a process where the when you have this kind of a collision, then the probe that hits the target sees first these nucleons which are here at the front, and then they kind of shadow the interaction probability with respect to the nucleons which are further away on the different side of the probe. And this is where the name shadowing kind of comes from. The really the way how people have modeled this and understood theoretically is more sophisticated than this very simple picture that I said here. But in any case, there is like a basic understanding of why this happens, but we would maybe like to understand the details of this better, and how does this shadowing relate to what is called the saturation effect, which also is expected to be enhanced in nuclei. So because you are packing more nucleons together, your gluon densities actually grow significantly. So if I jump ahead into here, you see that I divided my gluon distribution here with 208, so the number of nucleons. So if you would multiply with that value, you see that there are lots and lots of gluons in the lead nucleus, but per nucleon there are less than in one free proton.
Okay, good. Would you say the factor that they grow by? Do you have a sense for that? What's what's the dependence of this suppression though on A?
Yeah, so it seems that it follows also this kind of a power law dependence. So the heavier the nucleus, the larger the effect. So if you go to lighter nuclei, then there would be less suppression.
Okay, thank you. Then, okay, I have one last question. These nuclear modification factors that you introduced.
Yeah.
So do you introduce the one per PDF? Like so for quarks, there's one, and then for gluons, you have another one. Is that how it is?
Yeah, exactly. So this is like what we get when we parameterize our gluon distribution, and then apply the data to find how large our uncertainties in the parameters are, and this is what we get. And it's well, all of these have kind of a similar shape, but the details can differ. So the amount of shadowing can be larger somewhere, and then I actually seem to have picked a scale where they all look quite similar. But actually what happens is that the gluon distribution evolves in scale faster than the others. So if I would go to a bit smaller scale, the gluon distribution or modification would go down more than the quark ones. And yeah, so the modifications are not exactly the same, and one thing that we are trying to understand is how they differ flavor by flavor, and also maybe why that happens.
Very good. Any last questions from the audience before I take the chair's prerogative? Okay, super. So I do have one more question myself, if you don't mind, which is, so you were very conservative in talking about assuming that factorization still holds, for example, in DIS for nuclei. Have there been calculations that have looked into factorization for nuclei? Not so much this R modification times the nucleon PDFs, but just because the PDF is really defined as this matrix element. We have a proton and then some operators and then a proton on the other side. It seems to me like one could just replace the proton with a nucleus and everything would run through just as well. Or are there any potential places where the factorization might break there?
Yeah, so what is a question is, sorry, I need to jump back and forth, but if I go to this slide again. So as you said, we could very well expect that everything works fine if I just change my PDFs from proton to nucleus, nothing changes, everything works fine. But there are expectations that the higher twist effects would be larger in nucleus compared to proton. And this is still an open question. Does this really happen? There are good reasons to believe that this would grow with some power of A, let's say. And then there are people who build upon this and introduce things like coherent energy loss within the proton nucleus scattering, like Francois Arleo and collaborators have studied this kind of effects. And then the question is, are these effects large enough at the scales that we are studying in our global analysis or not? So since these are suppressed as a 1/q², as long as I'm at high enough scale, they should be negligible, do not affect my observables. But whenever I go to smaller scales, there is a danger that I introduce some higher twist effect, which was not included in my calculation. And this is also why we want to do global analysis. If we fit to many types of data at different scales, different x, if everything works fine and we get a very good fit on the data, then we can say that, okay, collinear factorization works very well. There seems to be no other effect. But if we see that some data does not agree within our global fit, then we can ask the question, is this due to higher twist effects? Maybe there is something more going on. And so this is still an open question, and why we want more data, different data types, to really compare and try to find how well does the collinear factorization work with the nuclei.
Oh, brilliant. Thank you. That was really great. Okay, so last call for questions. Yeah, Moane.
Yeah. Okay, so I don't remember what slide, but there was a slide in which it looked like you had these R's, and then you had the rapidity on the x-axis, and
Okay,
you had a statement. Yeah.
Let me see. So some of the data plots.
Yeah, I think it's later on.
Yeah. So
yeah, I think it's
was it this W production or?
I mean, there's that and the further one, but you were commenting on that you had less agreement at the higher rapidity, right? Like in the forward.
Oh yeah. So this one.
Yeah.
Yeah.
Firstly, can I understand what it is in the speak, and right, and then whether you have an idea for why you get these uncertainties in this forward reading.
Okay, so I didn't get the first part of the question.
I think that's the most important part. What are we doing here?
Yeah, so maybe what's on the y-axis and
Right. Yeah. So okay, so these were the same data as were in the previous plot. I forgot to say that. So same data, the digest production, and this was the double ratio. So you take the self-normalized data of proton lead, take the ratio with proton, and this is how you get this ratio. So it's the same data, and that was in that slide and here. And okay, and then we have the predictions or the predictions from ePPS 16. This fit did not include this data. Then we have the results of ePPS 21, where we included this fit. They constrained how large variations there can be in the nuclear PDFs. And then based on that information, we have a new uncertainty band, which is much smaller than before including this data. Is that all?
Okay, I think I might have to go read on my own first to fully understand what's going on. But
Okay.
thank you.
Well, we have another talk.
No
problem.
Okay, Petja, we've taken up a lot of your time. You've been extraordinarily generous. Thank you very, very much once again.
No problem. It was a pleasure. So
That was really, really great. Thank you so much, and have a great rest of the day in Jyväskylä.
And a good weekend.
thank you. All the best.
Cheers.
Bye.
Okay.